All right, so hello and welcome everyone to the third week of interactive live sessions for the course on fundamentals of convective heat transfer. This course is being offered by NPTEL and is being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I am a PhD scholar at IIT Madras, and like every week, we shall be solving some problems together and discussing uh, anything and everything related to the course. So, first of all, let me wish a very happy Independence Day to every one of you, and thank you for joining on a holiday. So, let's put our efforts together to learn something. Okay, so with that, let's get started. So we will, without any further ado, we will start with the first question of today's session, which is asking us the Faulkner-Scan equation related to boundary layer flow over a wedge is a what? Like, what is the type of the equation? That is the question. Is it option A, third order linear partial differential equation? Option B, third order nonlinear ordinary differential equation? Option C, third order nonlinear partial differential equation, or is it option D, third order linear ordinary differential equation? So there is no hurry. Read the question carefully. If you have any need for clarification, please ask. And once you have figured out the correct solution, you can either type it in the chat box or you can unmute and answer. As you feel comfortable, we can uh, do it that way. So this is the first question from my side, and from time to time, if you have anything to ask, please don't hesitate. So our third week of discussions or lectures, those were on broadly uh, based on the solution of boundary layer equations. So in the first lecture, I guess we saw how to simplify Prandtl's boundary layer equations to Blasius equations, and then how to solve it. Then we saw a similar approach taken to solve the uh, thermal energy conservation, which was known as Polhausen equation. And then ultimately we saw how the same concepts can be applied for inclined planes, not flat plates, inclined plates. For that, Faulkner-Scan equations show up there. So this is what this question is related to. The Faulkner-Scan equation related to boundary layer flow over a wedge is a what? Is it a option A, third order linear PDE, option B, third order nonlinear PDE, nonlinear ODE, option C, third order nonlinear PDE, or is it option D, third order linear ODE? We have one response so far in favor of option B, that is a third order nonlinear ODE. Let's see if we can get more responses. Okay, someone else agrees with option B as well. Let's see. I urge everyone to participate in this and at least make a guess in what the answer could be. Option B again. B seems to be popular. The Faulkner-Scan equation related to boundary layer flow over a wedge is a what? Is it option A, third order linear PDE, option B, third order nonlinear ODE, option C, third order nonlinear PDE, or option D, third order linear ODE? No more responses? Come on. It doesn't matter if you pick a wrong answer, but trying is important. Okay, so we got three responses in favor of option B. Let's have a look at the correct solution. The correct answer is option C, third order nonlinear PDE. Okay, sorry. This has been a mistake on my part. It would have been option B only, third order nonlinear ODE. So if I write down the equation, it looks something like this. So this equal to 0 would have been the Blasius equation, but we have uh, an additional term over here for the effect of the wedge of an inclined flow. So this is how the Faulkner-Scan equation looks like. First of all, it's third order because the highest order term is the third order, and it's an ODE, not a PDE, because all the functions are all the variables independent, or the dependent variable is f, and it's a function of the only one independent variable eta. So that's why it's a ODE and not a PDE. And these terms are, if squares or some products appear in a differential equation, then that equation is a non-linear equation, which is more difficult to solve. We already know, in high school math only we learn how to solve linear differential equations, but non-linear equations are an entirely different beast. So that's what makes things a little bit complicated. But anyway, there are numerical tools, very simple numerical tools, which can solve these equations with ease. So the correct answer would be option B, the popular choice, that is a third order nonlinear ODE, ordinary differential equations. Is it clear? Any questions on this?
Sir, option B is right.
Yes, option B is right. Here I have a mistake in my slides. This one should have been colored green instead of this one. Option C is
Okay,
not
sir.
right. Option B is the correct answer. Okay. All right. So, any other questions? No, right? Okay. So, if things are clear, we will move on. We'll move on to question number two of today's session, which is a numerical type question. It's asking us that for the given wall temperature variation for flat plate given as TWX equal to T infinity plus CX to the power lambda. This is the mathematical for. I'll write it down again. So TW, this is a function of x and is expressed as T infinity plus C x to the power lambda, where C is some constant. We can achieve uniform heat flux condition at flat plate for lambda equal to what? This is the question. What value of lambda? So let me pose the question correctly. So this is a flat plate with some TW. Now this TW is not constant, rather it's a function of x. So this is my x direction, this is y direction. I have a boundary layer forming, and the free stream temperature is T infinity. There is a free stream flow as well of U infinity. Now this is forming a thermal boundary layer, and as a result there will be some heat flux from the wall into the fluid, right? This is Q. Q double dash I'll call as flux. Q being the the rate of transfer of heat, and dividing it by the total area, we can get the heat flux. That is Q double prime. Q double prime has the units of watt per meter squared. Now the question is, this TW as a function of x can be written like this in this equation: T infinity plus C into x to the power lambda. The question is, for what value of lambda would I get a constant heat flux? So this won't be a function of x, but rather some constant. I hope the question is clear. Now you can take your time and try to find out what the solution would be. We have one quick response, that is uh, lambda equal to half. Let's see if we get some more solutions. Take your time, there's no hurry. So this is question number 2 of today's session. It's telling us that for a given wall temperature variation for a flat plate given like so, that is Tw of x is equal to T infinity plus Cx to the power lambda, where C is some constant, we can achieve uniform heat flux condition at a special case. Uh, what is the value of lambda for that special case? We have one response telling that lambda should be half, but we are waiting for more other responses. So, how can we try to even solve this? First of all, what should be our first step?
Sir, heat flux is equal to K into TW minus T infinity into root U infinity upon nu x into theta naught.
Okay, slow down. I'm a bit slow. So Q should be equal to T K into whatever is the temperature difference. Then what?
Sir, root
Root
U infinity
U infinity
upon nu x
upon nu x
into
hmm, out of root
theta prime into
theta prime
zero.
theta prime 0.
Yes, sir.
Okay, so first of all, how did we come here initially? So
This is the sir, expression of heat flux.
heat flux we can write like this as well, like fundamentally
Yes, sir.
k dt dy. This is the heat flux. So uh, let's see. Now, as a function, theta is the non-dimensional temperature, which can
Constant.
be written something like this, right? So now this T can be written as T infinity plus this TW plus, sorry, TW minus T infinity into theta. Then if I try to do dou T dou Y, which I actually need over here, then this is a constant. This will go to 0, and I'll get dou theta dou y over here, which I'll write as dou theta dou eta, because theta, as we know, is a function of eta, right? And dou eta dou y. Now eta we know as y into, what would it be? It should make sense this way. So u infinity x over nu, right? Am I doing this correctly? So meter squared per second and meter square per second. This is correct, right? The way I'm writing eta, or no? Maybe I'm wrong.
Yes, sir.
It should be u infinity upon nu x, I guess. Okay, so let's try to do this fundamentally. So eta I know as y by delta, and I know that delta by x is 1 over root rex. These are the things I know. So Rex is u infinity x by nu. So if I put this x on top, then delta would become uh, nu x over u infinity, right? So this would be reversed over here. So yeah, okay. So this would be the correct one. This is okay. So now this uh, dou eta dou y would then become simply u infinity over nu x, and uh, this value I know already. So this is at y equal to 0. So then this becomes uh, okay. Once again, I know this from this equation, the variation of temperature, that Tw minus T infinity should be equal to C into x to the power lambda. So this I'll replace with C to the power lambda. Sorry, C into x to the power lambda, and dou theta dou eta at eta equal to 0, because this is at y equal to 0. So this would be theta prime at 0. There is some number, some value which I can find out from solving the Polausen equation or whatever. And dou eta dou y, from this I know it equal to be u infinity over nu x. Sorry, nu x, yeah. So now Okay, from this equation, I can go over here. Then K will stay as it is, and this TW minus T infinity, I have already replaced it with C into x to the power lambda. Then the rest comes from this dou t dou y, which I solved over here. So the rest of it, theta prime 0, which is simply a number, and then I have this under root thing. So from here I'll take the x outside. So x to the power minus half. So I have x to the power lambda here and x to the power minus half here. Rest of it are numbers, mind you. So I'll club all the constants together and call that C prime, which is nothing but K into C into this theta prime into whatever this is root under stuff. So finally, and X will be X to the power lambda minus half. This would be my uh, heat flux. Now the question is, for what condition this heat flux will be uh, constant or uniform heat flux condition. So that means it has to be independent of x, right? Sorry, I wrote this incorrectly. This will be like this, x. Yeah. So this would be independent of x when. So I have this very simple algebraic form, this one. I want the condition at which this will be constant. This won't be a function of x. What is that condition? Anyone?
Lambda minus 1 by 2 is equal to 0.
Correct. So that means there will be no x here. I mean, uh, this thing should be equal to 1. When is it 1? When it's x to the power 0. So I can now put the indices together. Uh, so this would mean that lambda minus half should be 0, and very simply lambda equal to half would mean that my heat flux would now become equal to the C prime, some number, which is no longer a function of x. So that's why lambda equal to half would be the correct answer. Is the method clear? Any questions, anyone? Like, forgive my messy writing, but I hope I could make the process clear. Any questions from anyone? No? Okay. So then I'll assume that everyone understood this very clearly and lambda would be equal to half. Okay. So we'll move ahead. We'll move ahead to question 3, which is asking us which of the following is not an assumption for boundary layer flows. The not is in caps, so focus over there. Is it option A, Newtonian fluid flow, option B, high Reynolds number flow, option C, laminar flow, or option D, none of the above? So we have one quick response in favor of option D, that is none. Read the excuse me. To read the question carefully. It's asking us which of the following is not an assumption for boundary layer flows. So if any of the options is a valid assumption for boundary layer flow theory, then that won't be the correct answer. The options are option A, Newtonian fluid flow, option B, high Reynolds number flow, option C, laminar flow, or option D, none of the above. It's a very easy question. I'm expecting a lot of responses this time. Okay, so D has two responses so far. D again. Okay, we have one response in favor of option A, Newtonian fluid flow. Only five responses so far. What are the others doing? Sleeping? Am I being this boring? This is an easy question. Come on. You can either type in the chat box or you can unmute and answer as well, however you feel comfortable. But I will strongly urge you to at least participate. So this is question number 3 of week 3 of live sessions. So which of the following is not an assumption for boundary layer flows? Is it option A, Newtonian fluid flow, which someone has uh, said that should be the correct answer? That is, Newtonian fluid flow is not an assumption for boundary layer flows. Then option B, high Reynolds number flow. Option C, laminar flow. Or is it option D, none of the above? So, which seems to be the popular choice this time. Four people have said that none of the above are not assumptions, which means all of the above are assumptions which are taken for formulating the boundary layer flow theory. Okay, so let's have a look at the solution. The solution is indeed option D, none of the above. Now, first of all, let's consider this Newtonian fluid flow. So, what a Newtonian fluid is that the shear stress over there is linear to the gradients of velocities. That's all that a Newtonian fluid is. So, if you go back to the Navier-Stokes equations, so I'm writing this for the study case. This term over here, these two terms. These two terms won't be like this if it was not a Newtonian fluid. So this simplification comes from the assumption of a Newtonian fluid. So this won't be the correct answer. This is indeed uh, one very important assumption for developing the boundary layer flow equations, which are a subset of the Navier-Stokes equations. Then high Reynolds number flow. What this means is that Reynolds number has to be high so that the boundary layers are thin. So if Reynolds number is very low, what will happen is that this boundary layer would be very thick. The boundary layer thickness delta might be not negligible as compared to the length L. So how do we get that? We get that because delta over x we know that is proportionate to 1 by Rex. So if Reynolds number is low, this delta would be high in comparison to x. So their boundary layer theory doesn't really hold up. So the entire fluid domain would be covered by the boundary layer. So it doesn't make any sense. So that's why this is also important assumption. So that's why only this won't be the correct answer as well. Then laminar flow, of course, we are dealing with only laminar and you know unidirectional boundary layers. So there are turbulent boundary layer theory as well, which is not what we are studying now. It's beyond the scope of our syllabus as of yet. But laminar boundary layer theory is what we are studying. So their turbulence is also uh, not acceptable. We will only deal with laminar flow. So these three are important assumptions which go into boundary layer theory. So that's why none of them would be the answer, which is option D, none of the above. Okay, am I clear? Most of you selected correctly. So this Newtonian fluid flow, whoever answered, I hope I could clarify why it won't be the correct answer, right? Okay. So if there are no doubts, we will keep rolling. We will move on to question number 4 of today's session, which is asking us. This is again related to that Faulkner-Scan equation, the inclined plate flow or inclined flat plate. So for boundary layer flows on wedge-shaped body, the wedge angle beta pi and wedge parameter m, free stream velocity in such wedge flows is of the form, sorry, this would be written as u infinity should be equal to c x to the power m. This is how the free stream velocity is. So now the question is, what is the relationship between m and beta? Is it option A, beta equal to m by m over 1 plus m? Is it option B, beta equal to 2m over 2 plus m? Or is it option C, beta equal to 2m over 1 plus m? Or is it option D, they are independent of each other? There is no relationship between beta and m. So I'll draw the schematic simply over here. So this is a wedge shaped body and there is a flow past it. This is u infinity. Now this wedge angle, this angle is uh, pi into beta, and this u infinity over this over whatever boundary layer forms, the free stream velocity can be written in the form c into x to the power m. Now the question is, what is the relation? Whether there is a relationship between beta and m, and what is it? Is it option A, beta equal to m over 1 by beta over 1 plus m? Is it option B, beta equal to 2m over 2 plus m? Or is it option C, beta equal to 2m over 1 plus m? Or is it option D, they're independent of each other? Okay, so we have one response in favor of option C. Let's see what others have to say. Option C again. Option C has received 3 responses so far. 4. That makes it 5. Let's see what others have to say. Alright, so let us have a look at the solution. Solution is indeed option C. Everyone was correct. Beta is related to m as 2m over 1 plus m. So in terms of beta, what would be the how would we write m? So we can say that beta plus beta m equal to 2m. Then beta would be equal to m into 2 minus beta. So m would be equal to beta by 2 minus beta. Right? This seems correct, right? Any questions? Anyone? This is simply an empirical formula relating the two things. M is the, I guess it's called a wedge parameter, and beta is the wedge angle. Okay, alright, so we will move on. We move on to the question number 5 of today's session, which is telling us that for the given velocity profile, u by u infinity equal to 2 into y over delta minus y over delta squared, find the shape factor h, which is equal to delta star over theta, which is nothing but the ratio of displacement thickness to momentum thickness. So delta star is the displacement thickness, and theta is the momentum thickness. We have to find out h, the shape factor, which is a ratio of these two thicknesses. It should be a number. What number would it be? Would it be option A, 1/3, option B, 5 halves, option C, 15 halves, or option D, 2/5? These are 1 by 3, 5 by 2, 15 by 2, or 2 by 5. And this is the velocity profile given. You'll have to work this out. You'll need a pen and paper for this. Take your time. Try to find out the correct answer. one, I won't say answer, but rather answer as a question mark in its end in favor of option B, 5 halves. Let's see what others have to say. Okay. If you are having difficulties trying to solve it, please feel free to, you know, talk to us. We can discuss and try to approach it. Okay, we have another response in favor of option B, that is 5/2. If anyone has any doubts, you can ask. Please don't hesitate. Let's discuss and try to figure out what should be the right way of trying to approach this kind of a problem. Because this is a very common problem which you'll find in many exams. It could be, for this course, or these types of questions are very popular in GATE as well. If you know the trick, then it comes down to simple math. But otherwise, you could be struggling with it and wasting time behind it. Okay, we have one more in favor of option B. So those who are getting to option B, how are you approaching the problem? What is the first step that you are taking? Hmm? Three of you got the answer correct. Let's have a discussion now. We will have a look at the solution. The solution is indeed option B. That is correct. So all three of you were correct. Now, what is the process that you followed?
Sir, firstly, we
Yeah.
apply the formula of displacement thickness.
What is it?
And, sir, firstly, we apply the displacement thickness formula.
Yeah.
Then
Can
start.
you help me with the formula?
Sir, 1 minus small u upon capital U. Yes.
Rho eta, right?
Yes, sir.
Rho y, sorry. Same thing for momentum thickness as well. What is the formula for that?
So small u upon capital U,
Hmm.
and again,
U by U infinity.
yes,
Is this is correct, right?
To dy, yeah.
yes, sir.
Okay, so now we know what this u over u infinity is. We will simply plug those values in over here. So we will get 1 minus 2 into y upon delta minus y upon delta whole squared into dy. Same thing for this. This will be a bit more complicated. There will be a product of, okay, this would be plus. So y over delta whole squared. Then there is another u into u infinity as well. So this will get multiplied. Okay, so let's see. Now we shall integrate this. 1 will become delta, then this will become 2 by delta, and this is y square by 2. And y I'm simply putting in delta since the uh, starting limit is 0. So this is delta square by 2 plus this will be, there is delta square from earlier. Y square would become y cubed by 3, right? So this 1 delta will cancel out. This will be, I'm writing this as delta cubed only. Another delta cancels out. So 1 minus half plus 1/3. No, not half. 1 minus 1. 1 minus 1 plus 1/3 into delta. So this is nothing but delta by 3. And okay. So this would be a big one. So let's see. 0 to delta. First, I'll write down these two terms multiplied by 1. So that would be 2 y over delta minus y over delta whole squared. Then I'll multiply these two with minus 2 into y delta. So that becomes minus 4 into y by delta squared and plus 2 into y by delta cubed. Then I'll multiply these two terms with the last term of the first thing. So that would be plus 2 y by delta cubed minus y by delta to the power 4. This whole thing integrated. So now if I integrate this, the first term I will get is delta squared over 2. So 2y delta into delta squared by 2. Then minus this thing. If I make any algebraic mistake, please point it out. Okay. So this will be delta cube by 3 delta squared. Then the second term will be uh, 4 by delta into this is uh, delta cube by 3 and plus 2 into delta cubed 2 by delta cubed, and this is y cube. So integrating this would be delta to the power 4 by 4. Two more terms remaining. This will be again delta to the power 4 by 4. So delta to the power 4 by 4 delta cubed and a 2 from earlier. And the last term would be simply delta to the power 5 by 5. And I have delta to the power 4 in the bottom. So all these deltas would cancel out in a manner that all the orders are, all the terms are of order delta only, right? Because it has to dimensionally match. So theta becomes okay. The first term is 1 minus 1/3 minus 4/3 plus half plus half again, and then minus 1/5 into delta. So let's see. Half and half becomes 1, and we have 1 earlier, so these become 2, and minus of 1/3 plus minus of 4/3 would mean minus of 5/3, and I have minus 1/5 as well. So this will be 15. 2 into 15 is 30, minus 5 into 5, 25, minus 3 into delta. So this will become 5 minus 3. So 2 delta by 15. This is theta. So finally, the shape factor would be delta star by theta. Delta star we got as delta by 3, and theta we got as 2 delta over 15. So delta delta cancels out. 15 by 3 is 5. So the final answer is 5 by 2. Option B, correct. Any doubts regarding this one? Any questions?
Sir, is there any trick for this question?
I'm sorry, there is no trick. Like, unless, see, the main time taking part over here is the integration. So if you can find a trick to solve the integration quickly, then that would make the rest of the process easier.
Okay, sir.
Okay. So this is the only thing. Okay. So if there are no more questions, we will keep moving. We will, sorry, we'll move on to question number 6 of today's session, which is asking us that for boundary layer flows, if the fluid properties are assumed to be constant, the velocity field will be independent of the temperature field. Is it true or is it false? Okay. So someone is saying it should be true. Let's see what everyone has to say. So only saying true won't be enough. Can you tell why? You have to explain why. So let me make sure the question is clear. The question is saying that for boundary layer flows, if the fluid properties are assumed to be constant, then the velocity field will be independent of the temperature field. What does this mean? If I write it down in math terms, so the fluid properties are what? Density, then viscosity. So all I'm telling is this density is a constant, viscosity is a constant, and so on. Other properties also, like here, I don't think anything else comes into picture. But okay, the thermal properties we can consider. Alpha is a constant, alpha being thermal diffusivity. So if these are constant, then I'm telling that the velocity field will not have any connection with the temperature field. It will be independent of it. This is what the statement is saying. Now you have to uh, identify whether this is true or false and also explain why. So we have received two more responses in favor of option A. Why is it so? Or the way to prove something we learned in math is to assume the opposite, then show that that cannot be the case. Then we can say that okay, so the original thing must have been true. So this is called proof by contradiction. So you assume something opposite to the statement you want to prove, then you show that that is impossible. Then you tell that that means the original thing must have been true. Okay, let me ask a different question. In what kind of convection are fluid properties not constant? Is it option A, forced convection, or is it option B, free convection, also known as natural convection? You get the question, right? What I'm asking? Yeah, hi, sorry. You're saying something? What would be the answer to the second question? We will call this question number 6.5 of today's session. Okay, so someone is saying option A, forced convection. Option A, option A. So let's have a look at the correct solution for option C first. It is indeed option A true, so all of you had picked correctly. But I'll now go back to this second question which I asked in follow up to this. For this, forced convection would not be the correct answer. The correct answer would be free convection. That is natural convection. What happens in natural convection is simply this. So let's say you have a hot wall like this, and there is a cold fluid around it at T infinity. What happens is that this packet of fluid, let's say which is very close to the wall, this gets heated up and as a result of that, it expands. The density of it reduces. So rho is a function of temperature now. And since uh, okay, so let me write it down more mathematically clearly. So rho is a function of temperature, and temperature itself is a function of space, right? So there is a temperature field, what we were talking about there. So what happens essentially is that this packet of fluid, this gets lighter, the density of it reduces, and as a result, it experiences a buoyant force. So let's say, assume we are, taking a packet of lighter material and putting it inside a heavy fluid, so then it would experience a buoyant force in the upward direction, right? So that's the same what this experiences, and as a result, it sets up this convection current, and this again, goes up, cools down, and comes back again, creating this sort of a current. So here there is no, pressure gradient that is driving the flow. It is the changes of this fluid property, that is density, due to temperature, that is affecting the velocity field. So there was no velocity initially. It is the change in the fluid properties that is causing a velocity field. So in that case, it's this temperature field which is indirectly creating a velocity field. So that is the case where, free convection occurs and so on. But for simple forced boundary layer flows, there the fluid properties are assumed to be constant everywhere, and there the velocity field will remain independent of the temperature field. So option A would be the correct answer. Okay, I diverted a little bit over here, but I hope that the core idea is clear. Any questions on this? In the course, we haven't studied the natural convection yet, but we will surely go there towards, some of the lectures towards the end. Then we will get a better mathematical feel of it. But this is the physical mechanism by which convection currents are set up, and these are, very important for multiple reasons. The climate change which is occurring, and in many engineering applications also, where there is no, provision for flowing the fluid using some pump or something, there you have to rely on this natural convection. So having a good theoretical understanding of this is very important. Any questions on this or anything related to this topic? No, right? Okay. So we will keep moving. We'll move on to question number 7 of today's session, which is again a true false type question, which is asking us that at the leading edge of a flat plate, the boundary layer approximations are not valid. So this is a flat plate. This is the boundary layer on top of it. And this edge over here at x equal to 0, this is what I call the leading edge of the flat plate. The statement is that the boundary layer approximations are not valid over there. Is that true or is that false? So one response in favor of option A, true. Another response in favor of option A, true. So question number 7 of today's session is telling us that at the leading edge of the flat plate, the boundary layer approximations are not valid. Is that statement true or is it false? No more responses, only two. It's a very simple question. Come on. It's a true false. Another response in favor of option A. So let's have a look at the solution. The solution is indeed option A, true. Now the question is why? So three of you answered. Who can tell me why is it not valid? What is the main reason? Any guesses? Why not? So first of all, tell me what is the boundary layer approximation? What do I mean by that? Remember in scaling analysis we start with some fundamental assumptions about the boundary layer, about the shape and size of the boundary layer. What was that? So if I have a boundary layer like this on a plate of say length L and boundary layer thickness delta, then what is the relationship between delta and L? Which one is greater, which one is larger? What do we assume?
Delta is very small as compared to L.
Exactly. Right? So at the leading edge over here where it has just started, so there, you know, delta being much less than L also means some local delta x is much smaller than x. So let's say at a distance of a finite distance x, I have delta x as the boundary layer thickness. So the assumption is that the boundary layer thickness at the local boundary layer thickness delta x is much smaller than x, which is the actual displacement from the leading edge. Now at the leading edge, there x itself is very small. X tends to 0. So then this delta x being much less than 1 does not hold true. Delta becomes, x tends to 0, delta also tends to 0. So x and delta are of the same order. So there, this boundary layer approximation, this breaks down. So that's why at the edge, we can't say that our approximations are valid. Those are not valid over there. So that's why the correct answer over here would be true. Does that make things clear? Any questions, any confusions on this? It's a bit tricky, the concept.
Sir, please explain, sir, one more.
So I have, look at this figure. So I have a boundary layer forming like this. At some finite distance x, I have a finite, uh, boundary layer thickness delta x. And one of the assumptions I make is that this delta x is much, much smaller than x. So if x is, let's say, some 10 meters, then this delta x would be 1 millimeter, right? Now, at the leading edge, where it's just starting, I'll zoom in over here. So zoomed in view of this would be like, this is the edge starting, and the boundary layer is also starting like this. So this is x, this is y, and x is very small. X is very close to 0, and so is delta. Delta is also very small. So at the leading edge, x tends to 0, and so does delta. These are both very small quantities. Then we can't say that delta would be much, much smaller than x. No, we can't say this anymore. Is it clear now? Am I making sense? Okay. So I hope this thing becomes clear. If you have any further questions, we can discuss later as well. Okay. So we will move on to the last question of today's session. Uh, so this is asking us again for the velocity profile u over u infinity equal to y by delta. Find the ratio delta star by delta, where delta star is the displacement thickness and delta is the boundary layer thickness. This is similar to the shape factor question we did earlier. Simply, instead of shape factor, it's asking for a different ratio, delta star over delta. So will it be option A, 1/3, option B, half, option C, 5 by 2, or option D, 2 by 5? Okay, very quick answers in favor of option B. Give or take, say 1. Option D, half. It almost seems you were ready with the answer for this one. Have you solved this earlier? Or unbelievable speed. We are nearing the end of today's session and everyone wants to wrap this up quickly. Okay, we are flooded with options, responses in favor of option B. For the assignment, I think. Is this question common with the assignment? We are supposed to not overlap there. Okay, similar question was there. Was it the same or similar? If it's same, then I'm under trouble. Anyway, so let's have a look at the solution. It is indeed option B. Uh, we will quickly solve this. So we simply want the displacement thickness, as we can recall from one previous solution that we did, that this is the formula for displacement thickness. We know the form of u by u infinity, that is y by delta. It's a very simple linear boundary layer approximation. So let's say this is the boundary layer I know. This is u infinity, this is 0, and the velocity profile I'm assuming is linear. This much is delta, this is x and y. So I'm simply saying u by u infinity should be y by delta. Linear. Okay. But that doesn't matter for the sake of solving this anyway. So 1 becomes delta, and y by delta becomes delta squared by 2 delta. So this is nothing but delta by 2. So delta star by delta would be whatever. Delta star by delta would be half. Simple question, option B. Okay. So that's all for today from my part. If you have any questions, fire away. Okay, so if you guys don't have any questions, that's all for today. Happy Independence Day once again. Uh, we will meet again next week, and thanks for joining today.
Happy Independence Day.
Okay,
Thank you, sir.
okay, thank you. Good night.
Same to you. Thank you, sir. Good night, sir.
Good night, sir.